quick recap for those of you who weren't here on Friday. Welcome back. On Friday, we learned about a new distribution known as student's T distribution. Who was student? Anybody remember who student was? Guy that worked at the Guinness factory. He was part of the quality control. He wanted to figure out how much barley they had to sort of examine or look at to determine the quality of their product. You don't want to use up all of your raw ingredients because you still have to make some beer. So student came up with a distribution that allowed for small sample sizes. Okay. When we talked before about the Z distribution, we didn't really worry about how big our sample was, because we said, well, there's this thing called the central limit theorem that says as n gets bigger, lots of things in nature become normally distributed, like sample means. Well, Mr. T, well, I guess not Mr. Student, Mr. Student didn't have large sample sizes. He wanted small sample sizes. So what he did is he said, all right, well, let's introduce some uncertainty into the normal distribution. And what ends up happening is that when you have small sample sizes, the normal distribution gets shorter because more of the area gets pushed out into the tails. So if we compare the blue line to the purple line, we can see that they both have the same shape, but the only difference is in the variability of it. So our blue Z has smaller variability, so it's narrower and it's taller. Our T distribution has more variability, which means that it's a wider distribution and it's not quite as tall. Well, when you squish down the distribution, it plumps up in the tails. And because of the way that we do hypothesis testing, where we're putting our decision rule out in the tails, right? We take a 0.05 and we split it up and put it out in the tails, get it way out in the outliers. Changing the shape of the tails will give us a different result depending upon what our value of Z is. So that's when he came up with the T distribution. Don't ask me why he chose T. It's because of tails. There we go. Good job, Joey. I don't know if he's right. Did you Google that or something? Good job. Did you find out the value for me? Because I looked for it and I couldn't find it. Okay. So the tail distribution. You just messed up like 20 students if you made that up, by the way. Okay, good. I do that sometimes too. All right. So to find and use this T distribution, all we really need to do is pay attention to n. Otherwise, the formulas are exactly the same. Our variance, actually that's s, not s squared. Our standard deviation is the same, and minus 1 is in the denominator. That's sneaky. Our sample standard error is our standard deviation divided by square root of n. And then to find the actual value of t, it's the same thing as the z. We subtract the sample mean from the population mean and divide it by that standard error. So some of the letters have changed, but it's the same framework. It's the same step 1, step 2, step 3. Now, fortunately, for the most part, you're going to be given these things. Right? You're going to be given S. What you need to do is start to pay attention to N. If N is 185, do we need to use student's T? Not really. 185 is large enough that we can stick with the Z table, the normal distribution table. When you look at the T table, and you try to say, all right, well, I need to know how big n has to be. At around 38, so the upper 30s, then we start to go, well, it's about the same as the normal distribution. So what we did last class is we walked through how this works. I chose a different type of example from what we've been previously doing because we understand distributions. We understand what a t and a z is and how it finds us the area of the curve. And what we now start to need to do, what we should start doing, is we should start thinking about how we can take this probability distribution and link it to our hypothesis testing. And start talking about the area under the curve in a more probabilistic manner. So last class, we did this example, where we were asked, pick a decision rule. How sure do you want to be? The standard for political science and the social sciences is 95% sure. That gives us a 5% chance of being wrong. What interval contains the population mean given our sample? Well, all we had to do is think about this in terms of a graph. Right? We draw our distribution. I know it looks ugly, but that's okay because it's still a bell shape. Does not have to be exact. We used the information we had, and we determined what two values of x we think our population mean is in given our sample. Mute. We're going to run a class experiment. We're going to collect data on the Hillary Clinton feeling thermometer. Because we've already worked with this data before, we kind of know what we have for a standard deviation and what we have for a mean in the population. I can pull that slide up and we'll just pretend that's our population data. But let's see what this class is. So I'm going to ask you one at a time to come up here and type in a number for Hillary Clinton between 0 and 100. And then for something that I want to do later on in the class, if you're a male, I'd like you to type 1. And if you're a female, I'd like you to type 0. So everybody stand up, get in the line, and go up to the laptop. Everybody type in two numbers, and then sit down. 0 is cold. I hate that expletive deleted. 100 is I love me some Hillary Clinton, and I cannot wait to be her subject for the next 8 years. And then a 0 next to it if you're a female, and a 1 next to it if you claim maleness. And then we're going to see how well our sample in this room predicts what I'm going to claim to be the population sample that we got from the General Social Survey or National Election Study. So we are going to be the sample, and you all will be, the nation will be the population. Zero to 100. 0 is cold, 100 is smoking hot. I love Hillary.
Seems to be a trend.
Oh no. You're not going to make me fake the numbers, are you? I'm going to have 50, right? If you're neither, 50. If you're, yeah, she's okay, 75. Right? We talked about this before. If there's too many zeros there, I'm going to have to extrapolate some data. Do some bootstrapping. Also known as kind of making it up. Oh, you did it wrong. Okay, Clinton. What's with the zeros? Bunch of haters. 36. 85. All right, I'm gonna put Abby in here. Abby likes herself some Hillary Clinton. Okay. 1 0 0 0 0 0 0 1. That's whoever wrote 0-45. I'm gonna assume you meant 0 because you're a female and 45 because you like Clinton. You guys got that backwards. 1 1. Okay, who put 2? Somebody gave a score of 5 and then put a 2.
It's 2016.
I got binary.
Third option.
You were the third person. You were the only person that gave a 5. Admit it.
I was first. What do you mean?
All right. Well, I'm just going to give them a 1. We're going to assume a man made that mistake. All right. Let's save this. I'll save it later. Let's turn the screen back on. All right. We have a data set. Here we go. Uh, 20, 15, 5, 0, 45, 0, 65, 36, 24, 50, 50, 0, 85, 0, and Abby comes in at 100. So what should we do? I've given you data. What do we already know how to do? All right, let's find the mean. So the mean of Clinton equal to, I can do it in Excel, but I want you guys to tell me what it is. This is like reviewing. What would we do? Add what? Listen, don't get uppity. No, I want you to let me type on my own like an adult. So the sum of x is 495. And how many observations do we have? We have 15. So our n is equal to 15. Our mean is 495 divided by 15. Oops, I forgot the equal sign. Sure, now you're not going to be helpful. It's 33. Wow, you guys are rough. Okay. What else do I need to find out? Yeah, you got to do that. So how do we do that? Well, Clinton, that's my x variable. I have something called x bar, which is 33.0. And now I need to do, it's going back to our slides. I've got to find x minus x bar. Okay, easy enough. This is going to be called x minus x bar. And this is going to be equal to this one minus this one. Oops. And I'm going to go down through here and do this. Thank you. And now I need what? Nope. I got to square them first. So let's go over here. And this is x minus x bar squared, which equals this times this. Okay. Now what do I do? All right. I've got that. Now I need the sum. So I go back here. This is going to be my sum equals I got a really big number. Okay. What do I do next? N minus 1. All right, what's n minus 1? Okay. So I'm going to go over here a little bit. I'm going to do equals. And 14662 divided by 14. What am I going to do next? I got to do the square root of that. Okay, so I've done everything under the square root. Let's hope there's a square root function. Here we go. Give me the square root of that thing. Okay, so I now have my S. S equals, it's 32.36. Okay, now what am I going to do? Well, I have to find the standard error of my sample. So I'm going to take my S and I'm going to divide that by the square root of n. So standard error is equal to my, what's my number? My 32.36. And then I'm going to divide that by the square root of n. N is 15. Make sure I close the parentheses. And my standard error is now 8.36. We all good so far? All right, I'm just doing simple math. Following the equations. Now, let's see what our sample tells us about what we can guess the sample in the population to be. What was our mean? 33? Okay, so our mean is 33. Our n was 15. How many degrees of freedom do we have? We have 14. Degrees of freedom equals n minus 1. Now, how certain do we want to be when we're guessing at what the population mean should be around, given our sample? With what, how much confidence do we want to have in our prediction of where the sample mean should be? Do we want to do 95%? Okay. So we grab our t-table Now, for those of you who are looking at this for the first time, there's a couple of things that are different in this. The first thing that's different, the field of the table, those are the actual t values. So it's kind of reversed from the z-table, which had the z-score being your rows and your columns at the very top. Instead, the area is where you see t equals 0.1, t equals 0.05, t equals 0.025. Right? That at the very top, that top row, that's where the probability is. So you choose how much probability you want to have in the tails. And then you look up the corresponding t-score so we can see if we're in that area or not. Now, Joey, we said 95%, right? We want to be 95% sure of where the population mean should be. So we're actually going to use that middle column, that t equals, or the t score for 0.025. We're going to use that because we're going to put 0.25 in both tails. Which will leave 95% in the middle. Does that make sense to everybody? So if you want to, you can put a little arrow there in that middle column, because that's the one that we'll probably use the most. Homeworks could be tricky, and they could give you a one-tailed test, and they say, oh, put all of the area in this tail. Or they could use a different level. Our sample mean was what again? 33? Okay. So what are the values that, given our sample, we would be 95% confident that the population mean should be between those two values? Because again, we've only got 15 people, and we're trying to say what the rest of the world thinks about Hillary Clinton by asking 15 people. Well, 14 people and a toddler, essentially. I mean, I know she's 7, but she's still kind of tall or short. Right. So let's take a look. How do we do that? You already know how to do this. We were doing this when we were doing z-scores. The only difference is now we got a different number that we're using. We're not trying to find t, because the chart's going to give us the value of t. What we need to find is that mu. Right? We need to find mu right here. T for 14 degrees of freedom at 0.025 is which value? Looking it up on our table. 2.145. We have 14 degrees of freedom, so we go down to the 14th row, and we want that middle column to put 0.025 in each of the tails. So I go down, and then I go over, and I know that my t equals 2.145. I know what my x bar is. That was 33. I know what my my standard error of my sample is. Yes, keep. That was 8.36. But what I don't have is my value of mu. Because that's the value that I'm trying to predict given my sample. That's why we have this equation down here, where we've reconfigured it so that we're solving for mu by separating it out from the t and the x bar and the s. One other thing is that we're also trying to find the two values of our feeling thermometer that are on both sides of the mean. So we need to add that number on one side and we need to subtract that number from the other. So let's just go ahead and do the math. X bar is 33 minus t, which is our 2.145, times 8.36. I need a calculator. .145 times 8.36 is 17.93. Did anybody else get that? Or no, you're just all sitting here to see if I know how to work a calculator. Okay, so 33 minus, don't go, come back. Let's clear. 33 minus 17.93 equals 15.07. What does that mean? Well, sorry, it's at the bottom of the screen. 15.07. First of all, what is that 15? What does 15 represent? The lower bound of what? Yeah, right? 15 is a score on our feeling thermometer chart between 0 and 100. And Jake says, well, that's the lower bound. Okay. Given our sample, we would expect that the population mean is not lower than 15.07. Does that make sense? With 95% confidence. Now let's do it for the other one. We got to go all the way up too. That's this half of the equation. So we got 33 plus 17.93. That better be 50.93. Yeah? Ooh, no, keep that. Fit. 50.93. Okay, so what are we saying? Well, if you're going to guess what the population mean is in their feelings towards Hillary Clinton based upon you all, what could you conclude? Yeah, you all hate her. Like, even I made up Abby's score just to try to pull you guys up a little bit. Just a little tiny bit. Okay. So if we are the representatives of the United States, Hillary Clinton's going to have a really hard time to get people to like her. Because we don't like Hillary on this account, right? Anybody have in their notebook the number from before? Wasn't it like 63? Yeah, we're way off, right? We are way, way off. You all are not representative of the population at large. Listen, if you could just not call her a nasty word, Jake, I'll call that a win. Okay. So what does this tell us? Well, first of all, we shouldn't be making statements about political candidates based off of you all, right? Because this is a situation where our sample size of 15 is probably way too small. Yeah? Especially since the better answer is like 63, which in this would be way out here. So you're not a very good sample relative to the population. It also shows us the dangers of small sample sizes. And this is even with the benefit of using the t-distribution rather than the normal distribution. Because remember, with the t-distribution, we pushed that down and fattened those tails a little bit. If we were to do the same thing for the t-distribution, those values would be a little bit narrower because the shape of the curve is taller and thinner at the tails. Does this make sense? Have I properly shown you that bad things can happen with small samples? Okay. Now we do our best to acclimate to the small sample by, again, making the tails a little bit bigger, shortening the curve out, but this was not exactly the best room to do it. So let's think about it for a second. Why shouldn't I have expected you guys to get the population mean from your sample mean? What could I say about this sample that makes it more likely to get the wrong answer?
Well, we're in a classroom in a specific small micro community, whereas the question is encompassing somebody who would be otherwise elected by a much larger, more diverse cultural, maybe like coast to coast kind of a decision. So like people might think very differently here than they will in like Washington State or Southern California.
Okay. So we got a few potential sources of bias in here, right? First of all, this is not a national sample. This is the 14 people that are currently in this room at this time, plus my 7-year-old. Okay. So what we've done is this is not like bags of barley, right? Where there shouldn't be any concentrations to how the barley is sacked. You all are here for a specific reason. One, you're okay with attending college in the South, which would make you more comfortable in an area that is more socially conservative. That's one thing. You're in South Carolina. You're in Horry County, which is like 65% Republican. A lot of you are political science majors or Intel majors, which give you an additional level of interest in who the person of Hillary Clinton is. Okay? You are more aware of who she is. You are less likely to be ambivalent towards her. So that's why there weren't a lot of, it's funny because you're less likely to be ambivalent, but also for some reason you're less likely to like her. Again, it might be that knowledge thing. I don't know. I could also say it gave me more extreme viewpoints, so there were a lot of zeros in that data set when there weren't necessarily a lot of zeros in the population. That could be it as well. So there's a reason that you people aren't normal. And that could have had a factor in this. All right. I know the letters are just a little bit different, but the curve works the same way. Okay? Our mean is still the middle of the curve. We're still using a letter statistic like a T or a Z to figure out the values at a certain point out there in the curve. The T is just a little bit different because, like I said, you start with the decision rule. Right? You go, I want to be 95% confident or 99% confident. So you pick the value for your probability that you're looking for, and then you find the t-score that corresponds to that. instead of calculating the z-score and then finding out how much area is under the curve. Right? You are choosing how much area is under the curve first. That way you know where to place these boundaries. Right? You get to do that. Quite frankly, you can do this same thing with z-scores. It's just that you have to look it up in the table to find out which z-score corresponds to the level that you want. And we did examples like that. All right, with the test scores. We just gave you the score instead of you saying, oh, well, I want to know how, what the, what the lower 10% of people taking it. Well, then you pack all that 10% in that bottom tail of the curve. So this really isn't anything different. Now, I'm going to give you a little bit of a warning on the homework. It's long. There's like 32 or 34 questions, so you got to do like 16 or 17, and a lot of them have like parts A through F. So this is not something that you should start on Sunday night. And this is also the main way that you guys will be practicing for your midterm exam. So get started on this soon. I have office hours tomorrow. You're more than free to stop by. Okay. And with that?
Is it like a review of everything you've done, or is it just this T stuff?
No, it's everything.
Okay.
Which is fine because we're doing things like calculating means, which was homework number 2.
Yeah.
All right? So this all adds together.